So what we're going to be looking at in this video is we're going to start off by just with the basics of what a polynomial, what a polygon is, okay, and just some basic facts about polygons and the angles within polygons. So let's start off with the definition. Okay, a polygon is any closed shape that has only straight sides to it. So, for example, if there was any kind of curve coming off of any of these shapes, like a circle has, we would not call those things polygons. It has to be all straight line sides, and the shape has to be closed, right? So we can't have any opening so that you can get on the inside of the shape. And so I'm giving you some examples of things that are polygons. You're familiar with many of them. We have something that looks like a quadrilateral, right? A triangle, pentagons, hexagons, okay? So my question is how do we know how many degrees there are when you add up all of the angles on the inside of the polygon? So we call those the interior angles of a polygon. How do I know how many degrees there are when I find the sum of the interior angles of a polygon? So we're going to do a quick investigation here, and we're going to see if we can figure that out. Okay? So we're going to start off with a very basic fact. Okay? When you add up the angles of a triangle, we've done this in the past, we've proved this in the past, you always get exactly 180 degrees. Okay, so we're going to just say we're going to use that fact in order to figure out how many degrees there are in a larger shape and why. Right. So if I take a look at my next figure, this is a three-sided shape. We call those triangles. Okay, I have a four-sided shape, okay, which I'm calling a I'm calling a quadrilateral, and it might come in different forms like a rectangle or a square. Okay, but what we're wondering is how many triangles can you fit inside this quadrilateral, assuming that none of the triangles are overlapping each other? And the hint for this, in order to figure out how many triangles you can fit inside this quadrilateral, is to make sure that none of the diagonals that you're drawing cross each other. So if you take a look at this picture, it looks like I can only fit two triangles inside of this quadrilateral. And what I mean by no two diagonals cross is if you tried to say, oh look, hold on, I made four of them. Look, 1, 2, 3, 4. My claim is that you're not allowed to do that because you have triangles that are overlapping each other, and we're trying to figure out using non-crossing diagonals. So I couldn't use this one. I need to get rid of it and say there's only one diagonal that I can connect here for that to work. Okay, so we're claiming, okay, that the number of triangles that you could fit inside a quadrilateral is just 2. Okay, so let's continue that and talk about the next size, which is a pentagon. Okay, a pentagon has 5 sides, and if we're wondering how many non-overlapping triangles can you fit in a pentagon, what I'm going to do is I'm going to try to draw, okay, as many diagonals, meaning connect vertex to vertex, and keep doing that, okay, so that I don't have any overlapping parts. And essentially, if you were to try this out on your own, here's what you would end up with. Okay, this is the maximum number of triangles that you could fit inside of any pentagon that you drew. Because if I tried to connect this top one over here, I'd be going along a straight line that already exists. If I were to try to go down here, I would be crossing the red lines, and I'd be crossing the red lines. So there's really no other connections that I can make. So there's only 3 triangles in every pentagon. Okay, let's do one more. Okay, so here's my 6-sided shape, my hexagon. If I tried it, here's what I'd end up with. Okay, I'm connecting together vertices using diagonals, and there are only 4 triangles that will fit inside of any hexagon that you draw. Again, assuming that they are non-overlapping triangles. Okay, so let's summarize what we just did. Okay, what we claimed, looking at this little experiment, is that every triangle has 3 sides. Obviously, you can only fit one triangle inside of itself, right? There's no additional triangles, right? And so that has a total measure of 180 degrees, okay? Every quadrilateral has 4 sides. We could only fit 2 triangles in there, and 2 triangles would be 2 times 180 degrees, right? Each of the triangles has 180 degrees, so that's a grand total of 360 degrees. Let me write that in a different color just to save us some space. So you see, really what we're going to end up doing is counting the number of triangles that we can fit inside of these shapes, right? And that is going to be the total number of degrees on the interior when we add up all of the interior angles in any of these shapes. So let's continue. Okay, a pentagon had 5 sides. There were 3 triangles that fit inside, so that would be really 3 times 180. Well, 3 times 180 is 540 degrees. So what we're claiming is that every pentagon has a total of 540 degrees in it. Okay, and then if I were to do our last experiment was with hexagon, so we said 6 sides. We were able to fit 4 triangles in there. That would be 4 times 180. And again, if you do 4 times 180, you should get 720 degrees. Okay, so if you notice, there's a pattern happening here. And this is why we did this experiment, to try to figure out this pattern. If I talk about any polygon, which means I don't know how many degrees are in there, right, I'm going to say, let's call it n degree, or n sides. We don't know how many. The relationship between the number of sides in a polygon and the number of triangles that exist in that polygon is always the number of sides minus 2. So if you notice, 3 minus 1, or 3 minus 2 is 1. 4 minus 2 is 2. 5 minus 2 is 3. There's always a difference of 2. So if I were to ask you how many triangles are there in this n-sided polygon, the answer is there are n minus 2 triangles. And then, if you notice, there's a connection between the number of triangles and the total angle measurement. What we did was we took the number of triangles and we multiplied it by 180. The number of triangles, and we multiplied it by 180. So if my number of triangles is n minus 2, what I'm saying is we're going to take this expression n minus 2 and multiply it by 180 degrees. If you do the number of sides in a polygon, okay, and you multiply it by or subtract it by 2 and multiply it by 180, okay, that is going to be the sum of the interior angles of that polygon. So the sum of the measure of all of the degrees inside of a polygon, for every single angle, is always n minus 2 times 180, right? And that comes from really just the number of triangles that exist inside of that particular shape. Okay, so if I were to give you an example like this and say, find the sum of the interior angles of a 12-sided polygon. Okay, a 12-sided polygon is called a dodecagon, okay, but we can call it a 12-sided polygon as well. Okay, so what we're going to do is we're going to use our formula now. Instead of having to count, draw a picture and count how many triangles there are and multiply it out, we're just going to say, well, my formula said if I do 180 degrees times the number of sides minus 2, well, for this particular example, my n value, n representing the number of sides, is 12. 12 minus 2, right? Well, that would be 180 times 10. Okay, which that looks like 1800 degrees. So we're claiming that every dodecagon, every 12-sided polygon, has 1800 total degrees when you add up all of the interior angles of that shape. Okay, so there are several of these that if you want to try them out, essentially what we're going to do for each of these, and I'm not going to simplify, is I'm going to say this is 180. A nonagon is a 9-sided shape, 9 minus 2. A decagon is a 10-sided shape, so this is 10 minus 2. So you can see the pattern. Usually anything larger than, say, 12, we just call it by its, we call it an n-gon, and just state the number of sides. So a 24-sided polygon would be a 24-gon, and so we'd say that this is 180 times 24 minus 2. And so you can see they're very straightforward when we do these problems. We just need to plug in the number of sides into 180 times n minus 2. And that will give us the total number of degrees in that shape. Okay, so we can expand on this idea a little bit, and we can talk about what is the value of one missing angle. So if you take a look at this picture, if I were to say what is the value of a missing angle, the first thing I need to figure out is, well, what is the total number of degrees in this shape? So if I'm counting the number of sides, and as a suggestion, you might want to number the sides just so you don't skip one accidentally. I see 1, 2, 3, 4, 5, 6, 7, 8 total sides in this shape, right? If I want to figure out how many total degrees should be in here, I'm going to say 180 times 8 minus 2, and that should give me my total. So it's really 180 times 6. 180 times 6 is equal to 1080 degrees. Okay, 1080 degrees. Okay, so if I want to figure out what that missing angle is, I need to figure out, of the total 1080 degrees that should be there, how many of those degrees are represented by the angles that they gave me. So I'm going to add together all of the angles that are present in this picture. We're going to do 149 plus 125 plus 136 plus 88 plus 112 plus 217 plus 215. Okay, and it looks like I have 1042 degrees. So the sum of all of these ones except for the one that I'll call x, the one that we don't know, is 1042 degrees. So if I do 1080, which is the total number of degrees that should be there, minus 1042 degrees, it looks like I have 38 missing degrees, and so x in this case would have to be a 38-degree angle. But in order to figure out what that was, I needed to know what the total was in order to finish off my problem. Okay, so we have one more type of problem. Okay, and this is talking about the concept of a regular polygon, right? So we have three definitions here. Okay, equilateral is a phrase that we heard, or it's a vocabulary word that we heard specifically with triangles. We talk about equilateral triangles a lot. And what that meant when we talked about triangles was that all of the sides of the triangle were equal to each other. They were congruent. If we were to measure them, they would be the same length. So we're expanding that idea now, and we're calling an equilateral polygon a polygon where all of the sides are congruent. So it's the same concept, but just expanded to really not just three-sided shapes, but really any polygon. Okay. We can also talk about something being equiangular. If we have an equiangular polygon, then all of the angles of the polygon are equal. Okay, so that's just the same concept. Okay, so an example of that would be like in an equilateral triangle, all of the sides are 60, or all the angles are 60 degrees. So we would say that an equilateral triangle is also equiangular. Okay, and so if we put those two concepts together and say they're a polygon that is both equilateral and equiangular, which means all of the sides are equal and all of the angles are equal, then we have a regular polygon. Okay, so this is nice because if I give you tell you that a polygon is regular, I'm claiming that you should know the measure of all of the angles inside of that shape, and it doesn't matter how big the shape is, it's always going to work. Okay, so here's your quick summary of how we're going to find the angles of a regular polygon. So the first thing that we're going to do is we're going to find the sum of all of them. 180 times n minus 2, we want to know how many degrees are there inside of the shape. Okay, and then once we know that, because we know that regular polygons are equiangular, we're going to be able to say that all of the angles inside of that shape should be equal to each other, which means we're going to divide the total equally by all of those angles. So divide by the number of angles that exist. And then you can high five your friend because you got your answer right. All right, so let's take a look at an example here. So I have a heptagon here, and a heptagon, again, if you don't know your vocabulary for these shapes, this would be a seven-sided shape. If I ask what is the measure of the angles, which you might see this referred to sometimes as each angle, okay, each angle inside of the shape. If I wanted to know, like this one right here, which I'll call angle 1, what is the measure of just that angle? I'm giving you a picture that has zero information on it, and so you're going to actually have to figure this out all on your own, what the measure of all of the angles are. And so what we're going to do first is we're going to figure out what's the sum. If I were to add up all 7 of these angles, what should I get? And that's going to be, in this case, 180 times 7 minus 2. Again, 7 because I have a 7-sided shape. 180 times 7 minus 2 is 180 times 5, which is 900 total degrees. So I know that there are 900 degrees in this shape. But because this is a regular heptagon, regular means that all of the angles must be equal. That 900 degrees must be equally split by the 7 angles. So I'm going to actually do 900 divided by 7, and 900 divided by 7 is not a really nice number. 900 divided by 7 is about 128.6 degrees. So we're saying approximately, okay, not exactly, we're going to round to the nearest tenth, about 128.6 degrees each. This, if you were to add up 128.6 7 times, you're going to get about 900 total degrees, and that's the whole concept here, right? If we know that is a regular shape, we can take the sum of all of the angles, divide it by how many sides I have, or how many angles I have in this case, right? And that's going to be the measure of each angle of this regular polygon.